Okay, let's continue. I hope that in the first part I was able to demystify a little bit this blockchain ID. So I hope now more or less you know what the basic principles are. Again, there are many variants, and you might come across something which works different in certain cases, but I think understanding the main mechanisms and the main way of working is can really be beneficial for you. Another topic that I could not avoid, I think, when discussing some recent trends in enterprise computing information technology is, of course, artificial intelligence. When we open the news today, when we read any kind of magazines, artificial intelligence is there all the time. And also there, again, I want to demystify certain things. We'll see how far I get. But this idea of magic, and that it's all very magic and hocus pocus, and or that it can do anything. Let's try to bring a little bit of more nuance into that. And of course, the dongle doesn't work. Voila. One misconception is that people have the impression that artificial intelligence is something new, and that it's that's very recent, and that it is now happening, and all of that. Actually, that is not true. The first attempts in computer science to create artificial intelligence was in the 1950s. McCarthy, professor at Stanford University, and those days were still the days that most people did not have computer systems at home, and even a lot of corporations, companies did not have computer systems. But still, the idea was already there. How can we create some kind of intelligence in systems? How can we make computer systems intelligent? And there have some key defining moments that that people realized the power of those systems. Because of course, in the 50s and the 60s, there were some attempts, but they never really caught the eye of the big audience or the large audience, because it didn't appeal to the imagination of people. Now, there were some seminal moments in this whole history. In the left, and I don't know why normally it should pop up, but here you see Garry Kasparov, who was a world master champion in chess, and in 1997 he was playing a chess game against Deep Blue, one of the computers of IBM. And I mean, it's a pity that this part of the picture is not here, but actually here's a computer, and here's a guy executing the moves that are suggested by the computer. And at that time, people thought chess is such an intellectually difficult and complex task, no computer will ever be able to defeat world champions in chess. Well, in 1997, Kasparov lost some games against this computer, and people suddenly realized, wow, these systems are really powerful. Apparently, they can, if playing chess is intelligent, well, then apparently we can make these systems to a certain extent intelligent. Another moment came here when IBM Watson was created, where they were able to actually defeat the two of the most well-known and talented Jeopardy players, where you have this reverted quiz where you get kind of a description, and you as the player, you need to come up with the question. What is the question that fits the description that you have been given? And also there, a few years later, the systems from IBM Watson succeeded in defeating those world champions, or at least very good quiz players, in this quiz where people thought, well, chess is still something different than finding answers in a quiz. So the next major step was set. And then this symbol was not known 3 or 4 years ago, but now most of us probably do know this symbol. It's the symbol from ChatGPT, which was launched by OpenAI in 2022, where we even went one step further, where suddenly you could have conversations where you could ask questions to something looking like a chatbot and you would get answers, and those answers, they seemed very much human-like, and they actually were solving questions and providing answers to things. And people said, well, is this then real artificial intelligence? Well, it depends on how you define it. As I said, in the mid-50s, Carty in Stanford University defined artificial intelligence as the science and engineering of making intelligent machines. The question is then, of course, what do we define as intelligent? Well, a very well-known mathematician and computer scientist, Alan Turing, he defined at a certain point in time the Turing test, where he said, well, if we really want to test whether a machine is intelligent, yes or no, well, then that computer would be able or need to be able to deceive a human into believing that it was human. Put briefly, suppose that you have two computers and you're sitting next in front of them and you're having a chat conversation in that computer and you get always a reply. So you type something into the computer, you hit enter, you get a reply, and you do that on two computers. But in one computer, there's in another room someone replying to you, a real human. And in the other computer, there's just software. There's a piece of software answering to your questions. Well, if you would not be able to make the distinction like this computer is providing me answers from the human and this computer is providing me answers based on the software, Alan Turing, probably one of the most smart people we ever knew in the computer science field, he said, well, if you are able to pass that test, then you really have intelligent machines. To be debatable, probably today, some systems, ChatGPT might have passed this test. So yes, some very big steps are undoubtedly being set in this domain. More or less summarized, I think a good definition nowadays for AI would be the fact that we try to make systems that exhibit human-like behavior that we interpret as something that is typical for a human person. Yeah? To recognize certain things or to do certain things, to generate certain things. Can be vision. We can see something and we can recognize it. I mean, babies of a few years old, they are able to generally to recognize their parents, to see what is an animal, and later on they will be able to see what is a cat and what is a dog. Imagine how difficult it would be to program it in the language that I showed you in the first lecture. Have two numbers, add them up, print them, store them somewhere. Yeah, the distance of calculating some numbers and printing them versus looking at something and recognizing whether it's a dog or a cat. Programming that, I challenge you, it's not so easy. So it's very human behavior that we can actually do that. At a very young age, we can recognize objects, and this is something where computers up to a few years ago were not able to do so. Although they had a lot of calculating power. Same goes for sound, recognizing a song or making some music. A text, reading a text, generating a text, or any kind of advanced reasoning. Logical reasoning, but in an advanced way. Some people use it a bit popularistic by saying everything which is not yet possible in informatics. But that one I find not so well of a definition, but many people will have different definitions. I think this one is not so bad. It goes into the direction that we should have. The second thing that I want you to be aware of is that when people talk about artificial intelligence, it's a broad concept, and artificial intelligence can mean a lot. And this is a picture that, again, I'm not the first one to put it forward. A lot of people use a similar classification, but it's important here to realize that a lot of concepts are used in this context. Some of them are similar, and some of them are really different. If we talk about artificial intelligence, there are many techniques that fall under artificial intelligence, that fall under the fact that we try to have human behavior, human capacities, which are which can be performed by systems. On the one hand, we have inference engines or expert systems. Today, no one talks about them. Although, when I was talking about the 50s and the 60s, this McCarthy, they were actually explicitly doing this. They were going for the fact that, well, how do you suppose that you wanna see whether you want to give a prospective client in a retail bank a credit, yes or no? Well, you can have a human person making that decision and thinking about, what is the risk that the person cannot pay it? And then we will probably see what kind of job has the person. Is it a fixed contract or a temporary contract? Does the person already have any debt? Maybe you can look into the history of that person, whether they were always very, very reliable in paying their debts and so on. And so you could mimic that one way or the other by providing fixed rules to the system. You could mimic that behavior. You could say, well, if the income is about a certain amount of money, well, then you can ask, do you already have car payments? If the car payment is less than 10%, well, then we continue. But if the income is below 50,000, we say, no, you don't get the loan. If the car payment is above 10%, we say no. But if it's less, well, we can, for instance, also say, okay, do you already have the mortgage payment? Is it less than 20% of your income? Yes, okay, then we go ahead. So you can replace certain rules that humans use to make certain decisions. You can make them explicit and to define them into systems. There are some drawbacks there. As we said during business process reengineering, when you want to analyze a company and processes, often a lot of this knowledge is tested. So even if you ask people, how do you make that decision? They will often not be able to make it explicit. It's also very costly because some of those decisions are very easy, but if you would ask a medical doctor what all the rules are that he or she uses to diagnose someone, well, they have these 6 or 7 or more years of study and they all absorb it. And based on that, taking all those things together and also with their experience and sometimes even their intuition, they come up and they say, probably this is the disease you have. And I would, in your case, go for this treatment. Well, putting that all into a system is quite difficult, quite extensive. And of course, that even changes throughout time. So even if you would succeed in making such kind of a system, the situation might change over time. Medical knowledge progresses over time. So each time that new information is there, you would also need to adapt your system. But it's a very important subclass of artificial intelligence. And when people today in the media and so on talk about artificial intelligence, they often neglect this one. So today, the biggest advantages or the biggest steps forwards are made into this right part of the Venn diagram, which is as such, it's okay, but it's often not explicitly mentioned that they are looking at this subsection of artificial intelligence. Now, when we look at this right part, we see like the biggest one, the encompassing one, is called machine learning. And when people do talk about artificial intelligence, they mean machine learning. They say artificial intelligence, they mean machine learning. And to demystify it already a little bit, everything that you see in terms of machine learning is nothing else than looking at patterns, recognizing patterns, generating patterns. That's it. These systems, they do not understand anything. They do not have some kind of a soul. They do not have any intention. They even don't know what they see, what they say. They look at patterns. They are very good at recognizing patterns, and they can generate similar patterns so that it looks as if they understand. Also within machine learning, there are very different approaches. And I mean, artificial intelligence, it could be a course on its own, it could even be a full master's degree on its own. So, I mean, I just can highlight certain things here. There's often a big distinction between supervised learning and unsupervised learning within machine learning. Yeah, supervised learning being the fact that it's supervised, meaning that you give information to your system and you label it. Again, if you want to make a system that recognizes whether it sees a dog or a cat, which is a typical example that data scientists like for one reason or the other, you give it a lot of pictures, and we humans, we start by labeling each of those pictures. This is a dog, this is a cat, this is a dog, another dog, a cat. So we give it pictures, we label those pictures, and we give it to the system. We could, for instance, also give a description of sets of houses. We say this house did so many square meters at this price, so many square meters this price, so many square meters this price. So with supervised learning, we give a data set to the system and we tag it, because that's also important. Everything on machine learning is about recognizing patterns and generating patterns. And the only way you can recognize patterns and generate patterns within an information system is to give it lots of data. Lots of data. And if you do that in a supervised way, you give the data and you label it. The other way is to have unsupervised learning. Unsupervised learning is still you give a lot of data, a lot of training data to the system, so that it can recognize patterns, but you will not label it. You will just give it to the system and you ask, look for patterns. Look what you can find. There are some other categories as well, like reinforcement learning, where you ask the system to optimize something. For instance, if you have airline ticket systems, you might say to the system, determine the price based on all the context that you have, the day, the amount of users, the remaining capacity of the flights and so on, but try to optimize your profit, for instance, and then the system will adapt the parameters of the price and the timing of the price depending on what it has experienced in the past. You can have association rule discovery systems, which is the system that you often see when you go to some kind of a web shop and they say, well, you're having this in your basket. Maybe you're also interested in this because this is a very nice complement to the product that you already have. The way how these systems propose that is also by interpreting a lot of past data, past transactions that other customers did in the previous days and months and years, and by doing that they recognize patterns and they propose them to you as well. Or anomaly discovery, and so you give a lot of data to the system and then you try to see, does something fit into this already existing set of data, or is it strange, is it an anomaly? Yeah. But most popularly, people talk about supervised learning versus unsupervised learning. Now, I've made them a little bit graphical here, and some of you might already be familiar with some of them, depending on your previous studies or even your trajectory before. But I said here, like, okay, we have in supervised learning, typically we talk about classification and regression, and unsupervised learning, we talk about clustering. I try to make it a little bit visual here to make it easier to understand. Regression, and I simplify here a lot, regression is the fact that you might have seen it in your basic statistic courses, that in one or based on one or multiple values, and here we have the simplest situation, we have one variable. Based on that one variable, you try to predict another variable. So based on the X value, you try to predict the Y value. And how do you do that in regression? Well, you have all these blue dots, which are the data points that are given. For instance, we know from a set of transactions, the amount of square meters of a house, as well as the price. And so the amount of square meters is the horizontal axis, the price is the vertical axis. And if you have many data points, if you have many blue dots, what regression will do is it will try to see the pattern between those two variables. It will try to fit some kind of a curve here, and in such a way that that curve can be used to predict new dots on your own. So suppose that another house is being put on the market and you know the square meters, that based on this curve that you know, okay, most probably this is going to be the price. Yeah? So the idea of regression is you take data points and you try to find some kind of pattern, you try to find the link between the input and the output variable. if you have seen some things before in statistics, this is kind of the very easy basic model of linear regression, where you say we try to predict the y variable, the price, and we do that based on an intercept, which you see here, one input value being the square meters. Here you have one parameter, which is the angle of that curve that you try to estimate. And then, of course, you might also have an error. You might be, with your prediction, very, very correct or very, very wrong. That's regression. You have one or multiple parameters, and based on those parameters, you try to predict another parameter. Classification is similar, but different in the sense that you try to classify something. Yeah? You have, for instance, dots, which are the blue dots, which are on the right of the curve, dots which are on the left of the curve, and with classification you try to see what makes this difference. As of when is something green, and as of when is something red. And with clustering, whereas with classification the data is labeled, so you know upfront these are green spots, these are red spots, and we try to make a good machine, a good device that can help us in making those distinctions. With clustering, we don't tell the system up front which are the blue, or which are the green ones, which are the red ones. We ask the machine, we ask the software system to do it ourselves. Yeah, and so classification and regression are supervised. Clustering is unsupervised. Examples of the usage of classification is, for instance, an email that you get into your mailbox. Is it spam or not spam? That's clearly a classification. It's either this or that. A person who wants to have a mortgage with your bank, is this person creditworthy? Yes or no? Regression, as I said, you try, for instance, to predict the price of a house, or you try to predict the number of passengers wanting to buy a ticket on day X. You have historical data, and based on the data, you try to make predictions for the future. Unsupervised learning, there the data is not labeled. You can use it, for instance, for customer segmentation. I give a lot of data about my customers, and I ask them, okay, give me some proposals. How should I cluster my customers, having several similar preferences, having similar characteristics, and so on. What's interesting here to see is that this kind of, so here you see this line, which is described by this mathematical function. The way how this line is calculated, if you had statistics, you will know, is what it will do is it will try again. It will try a lot of lines. You will try out a lot of lines. You will try this line and this line and this line and whatever. But in the end, you will end up with a line which looks a little bit like this. And how is a system, how is this software able to do that? Well, it will try out all these lines. And for each of those lines, for instance, this one, it will look at a certain point. It will see what was the actual value, this price. What is the value that my line that I'm trying out here actually delivered in terms of value? It will never be exactly on the line. There will always be a little bit of a difference. There will be an error. So we take that error of the estimation, we square it, because some of them are negative, some of them are positive. So we square it so that it is always positive. And the further we go from the line, the bigger the value becomes. So the more penalty that the system will give. We do that not only for one blue dot, we do that for all the blue dots. So we sum them up here, and we try to minimize those errors. So what a regression system does is it looks at all the blue dots, it tries out several lines. In each of those lines that it tries out, it looks at the errors. How good is the curve fitting the data points? We tried it out for different lines, and we choose that one that has the minimum squared errors. So there's no hocus pocus there. It's just calculation. It's statistics. You try things out. You calculate the errors. You square them. You sum them, and you try to minimize it. So far, so good. Okay. If I want to put that more graphically, you could think about it like that. You could say, well, we might have some input here, some input layers. For instance, we could have the square meters of the house, but also the location of the house, and maybe the energy efficiency of the house. So we have certain input parameters, and based on that, we try to predict, for instance, what type of house is it? Is it an apartment? Is it a villa? Is it something else? Could be some kind of a classification problem. So we have some input, we have some output, and what those systems try to do, what regression or what classification also tries to do, is it will try to look for the relationship between the input variables and the output variables. Could be, for instance, that if you are a villa, if you are looking at a villa like a nice big house, well, then of course that will be highly correlated with the fact that that house is quite big. But if you're with an apartment, for instance, okay, that will be less linked with this one. Or if you are in a certain location, like a city, well, then in a certain city, the chances that you are having a big villa standing on its own are much lower. So having something in a big city is then, for instance, much correlated with an apartment, because big houses do not occur so difficultly. So you have input variables, you have output variables, and each of those output variables is connected with each of those inputs, but some of them really determine much more the likeliness of a house being an apartment or a house being a villa, or some parameters much more clearly define the fact that this house is in a city, or this house is an apartment or a villa because it's either in a city or it's big or small. So we try to make a connection between input variables, output variables, and we do that by connecting both dots. We connect the input with the output. All of them are connected with all of them, but some of those relationships are very strong. Some of them are very weak. Yeah. Now, up to now, we've seen machine learning. And machine learning, of course, why does it say machine learning? Well, it's learning. It means that this is statistics, which you might know. What is typical for machine learning is that, of course, first of all, it will often not be one variable, which you can nicely present in 2 dimensions here, but it will have more variables, of course. But it will also learn. It will adapt these parameters as the system gets more and more data. It will adapt the thickness of those lines as it gets more and more data. So it's predicting a classification, it's predicting a certain regression problem, it's predicting a clustering problem based on data, based on several input variables, and it learns. It adapts its parameters, it adapts its algorithm to do that prediction based on the data that it gets. So the learning stuff is actually optimizing prediction parameters. Now, if we go one step further, so we've said, okay, within artificial intelligence, we have machine learning. Let's take a look at neural networks. What are neural networks? As you can see here, neural networks are a specific type of machine learning. And they are the specific type of machine learning in the sense that they focus on similar problems. They focus on regression. They focus on classification problems as well. But they will most likely do that on unstructured data. Up to now, we've seen structured data. If we try to predict the price of a house and we go for the square meters, the location, the energy efficiency, those are all structured data. It's basically a number. Square number, 20, 40, 100 square meters. The energy efficiency, 80, 100, 200. It's structured data. Unstructured data is data that you cannot so easily summarize in 1 or 2 or 5 or 10 variables. Because how would you do that for text and for video and for images? Nevertheless, that's what deep learning tries to do. They will say, well, maybe if you have a picture, there's not 1 or 2 numbers that actually summarize it. But what is a picture actually if you look at it on the screen? How is it represented? What is suppose that I would display an image here. Bits, yes, and more specifically, that image that will be divided into small pixels. Yeah. So it will be a square, and it's a table of pixels, and each of those pixels, they have a color, and that color has a certain numeric value. So indeed, you're right. In the end, we can derive text and images and videos to ones and zeros. We can. The problem is that it's not structured. It's a lot of variables, because if we have a big picture, we have many pixels, and for each of those pictures, we have a color value. So it's not structured, but we can still convert it to a digital alternative. And what those deep learning mechanisms will do is they will say, well, let's try it anyway. Let's try to look at unstructured data and try to look at classification and regression problems nevertheless by converting that unstructured data to numeric values. Describe all the pixels, and for each individual pixel, we will give a color code. But what happens then is that these nice, simple figures, which even here are too simplistic because they only consider one variable, and you can also have multiple regression and so on. But in any case, this picture where you have input layers and output layers and you directly connect them, that doesn't work anymore. Because if you look at a picture, I mean, the upper left color of the upper left pixel and its color, to make the connection whether it's a cat or a dog, that doesn't work. That's too complex. So what then happens is that they use neural networks. They will use the same processing, they will use the same ID, but they will say, well, we will not make one layer of regression. We will put hidden layers in between. We will put something like that. So we will not just do one regression, we will do many regressions. We will do many interpretations, many hidden layers here, and maybe the system will recognize certain things, like this might be an eye, and this might be a nose, and this might be an ear. We don't know. Maybe the system will not. But we give it the possibility to do many regressions after each other. Yeah. Why is it called neural networks? Well, because they say it's inspired by the human brain. Partly that is true. The human brain indeed works with neurons, which are nodes, which are elements in your brain, and they work on electricity, so they're connected with each other, and one neuron can fire a small electric potential, and it will fire, or it will connect with some others. So it has some similarity, but of course the brain also still has many other complex additions to that. So it's inspired by having this network of neurons, and it's called deep because, yeah, deep learning refers to many layers of regression. And so what will happen is that instead of having this direct input-output link, you will have many hidden layers. And then the question is, how do you go from one layer to the other? That's the question. How do you do that? Well, to start with, you define your input layer. So you have a potentially enormous amount of input layers. For instance, you have 20, 30, 50,000 pixels. For each of those pixels, you define the gray value, for instance, or the color value. And you have potential outputs, dog or cat. Or if you have a dice, you can have 1, 2, 3, 4, 5, 6. And what you will do then is you will define nodes, the input, the output, and hidden layers. And you see that each node is connected with all its preceding nodes. So you have nodes and you have connections between these nodes. And we have that here for this one, we have it for this one, we have it for this one, we have it for this one, not only in the first hidden layer, but also in the second one, in the third one, and in the final one. What these neural networks do is the same as we saw for machine learning, but then on multiple layers. So each time they will be fed with a lot of data. They will be fed with a lot of pictures of cats and dogs, and they will know, okay, is it a cat or is it a dog? And then they will try out to give values, to give weights to these connections. They might say, well, this pixel, this generates a high value for this, and this is a high value for this, and maybe a low value for this. So what they will try to do is, instead of just trying to estimate this one little parameter, this beta, in a simple linear regression, they will try to estimate a good value for all those connections. And each connection, each node, how does it determine its value? Well, it will look at all those preceding connections. It will look at the strength of that connection. Is it strong or is it weak? There will be a numerical value from often between 0 and 1. It can be a very weak one. 0 can be a very strong one, which is a 1. And it will multiply that with the input value. So each layer determines its value based on the preceding layers. And what neural networks then do is we give a lot of input, we label, if it's supervised learning, we give them a lot of outputs, and we just let the system try out. They will try different values for those lines, and they will try to reconfigure, and they will see which configuration of lines will give them the best output. Just as we said here, linear regression, it tries out different possibilities, and then it will look each time, with each attempt, they will calculate those errors, and they will choose in the end the line which has the lowest error. That's the same for these neural networks. They will be fed a lot of training data. They will try out different kinds of weights with often a different amount of hidden layers, more, less, and so on. And they will try, and they will look, and they will compare, and they will go for that model that has the lowest error. And based on that, based on those magical functions, it appears with a lot of trial and error, more hidden layers, less hidden layers, well defining your input variables and so on, making sure that you've adequately labeled data, it appears that in a lot of cases, these kind of neural networks are indeed in the position to recognize images, to recognize certain sound, and so on. If you look mathematically at this is all that happens. This is the and of course I will not ask you to do any kind of mathematical proof on your exam, but if there's someone with like a more engineering kind of background, this is actually only what happens. How do we go from one layer to another? How do we go from H0 to H1, and from H1 to H2, and H2 to H3, and so on? Well, we take the input values. So for all the pixels, we take the values. We multiply them by a set of weights. So the first pixel, we multiplied by the first weight. The second pixel, we multiplied by the second weight. The third pixel by the third weight, and the end pixel by the end weight. And we do this matrix calculation. Based on that, we have a first value. And then there are some complexities in the sense that there's sometimes a bias that determines how quickly will we fire, how quickly does one node fire to the other node. And we will also do some transformations, often with sigmoid functions, so to be sure that the values are not just whatever it can be, but always nice between -1 and +1. And we will look for a cost function. So each time we will see, with each attempt of this neural network, we will see how good or how bad is it. And we will give it millions of examples. And each time we will see how good, how bad is it, how good is our projection with the actual output. And so we will look for the set of weights, set of lines, how thick or how thin they are. We will look for that set of weights, that set of lines that has the minimal cost, that is as close as possible to the correct answers that we know from the labeled data. So in the end, in order to demystify a bit, these neural networks, they are nothing more than a lot of matrix calculations. So there's no real understanding in this. There's only matrix calculations. That's also the reason why you see these days that this new generation of chips pops up, and that some more traditional companies like Intel and so on are having a hard time, because the kind of processors that you need to do these calculations, the traditional processors are not very good at it. You need to have processors who are doing these kind of matrix calculations a lot and a lot and a lot. Yeah. Let's go one step further. we said here we have machine learning, neural networks, large language models. These are basically the things that you see with ChatGPT and so on. They are basically exactly the same, but specified or attuned to one specific application in the field of artificial intelligence, focused on text. Yeah, and just as with regression, just as with classification, what these large language models do is they try to predict. They do not try to predict, is it a cat or a dog? They do not try to predict what is the price of a house. They try to predict what is the next word in a sequence of text. So for some, that might be a very sad conclusion, but again, there's no real understanding of the text by those algorithms. They just try to predict the next word. How do they do that? Same as before. They have a huge amount of training data that is thrown at them. They will interpret the data. They will make long lists for each of those words, like what is the typical word that comes before, what is the typical word that comes after, and they will interpret a lot of text. And based on that input data and the associated output, knowing what were the preceding words, knowing what were the words that are coming after, they are very good at this time predicting the next word. And so when you do that not only one time, when you have a text and you not only predict the first word, but also then you redo the same trick. You take the text with the additional word, you take everything together, and you again predict the next word. And you take the next word with all the preceding text, and you again predict a new text. Well, then these systems can be trained to such an extent that they indeed are able to generate meaningful, useful text. Most well-known examples are like these GPT systems, which are, it stands for generative in the sense that they will generate text. They are pre-trained because if you would think about it, it still doesn't make sense that you can ask a question and that you get a reply. Because if I talk about predicting the next word, normally, if you do not train it with human feedback, it will just make the question longer and longer and longer and longer because it looks at the text that was there and it will add some additional text. That's what it's programmed for. But so you need some human additional pre-training there to say, well, if you have a question, you also need to make a reply and you need to say thumbs up, thumbs down. That's often basically the reason why you see in those chatbots, you still have the possibility to indicate whether it's a good or a bad reply. They will use that human feedback to optimize themselves. And they're kind of in a transformer model as well, in the sense that those systems, of course, what I explain here is like the very, very basic and the main mechanism. But in order to really get to useful results, you need to tweak and fine-tune it a bit. And what they did, for instance, here with these transformer models is to make a system so that the algorithm also knows what are important words in the text, what are less important words in the text. So they optimized it a bit by human pre-training and by applying these transformers. But in essence, the underlying mechanism is we know a lot of text that's out there on the internet. Based on that, we cannot predict whether it's a cat or a dog, whether the email is spam or not spam, or so on. We just predict the next word, and based on that next word, we make a text. That's also the reason why you can have a lot of these hallucinations, because it will predict the most likely word, but it will not, as such, really understand the text. So it might come up with something that sounds very sensible, that sounds very plausible, but is still not correct. We've seen this in several cases, and these are actually old cases already. So several years ago, they were already doing similar stuff, not at the scale of ChatGPT, where they try to generate articles, and people were not able to distinguish between a journalist writing an article and a computer system writing an article. And now, of course, with ChatGPT, it's even much, much better. And so you can create easily automated reports, corporate communication summaries, and sometimes you might even claim that the text written by those large language models, they're even better than human written text. You can also use it the other way around. In a business perspective, again, if we're reflecting on the business value, we see that these days you can, for instance, use these models also to do sentiment analysis, to look at the tweets that are sent around your company or a person or a product, and to see, are people positively commenting on my product, on my organization, or negatively. You could look at blogs, you could look at other resources on the internet, and really try to sense, okay, what is kind of the sentiment here? Because again, being fed with a lot of previous data, knowing whether it's a positive or a negative expression, they are able to classify these things, just as you are able to classify spam versus non-spam. Speech and recognition, also there were very easy or simple outputs. Like nowadays, if you walk around in a Belgian station, they will automatically generate sound for you, and it's even there. It's quite prefixed, quite programmed with rule bases. But nowadays, you can also have a full speech and sound recognition and generation, which has in the last few months even significantly improved. And you have this Shazam thing, which was introduced already a few years ago, which I, at that moment, also find already quite impressive, because if you have a sound or a song and you have the system listening to it, it will automatically recognize it. You can generate images. This one is from DALL-E. I think it's 1.5 years, 2 years ago that you were able to do these first few attempts where you ask, okay, I want 2 of these what it's called again, not mangoes, avocados dancing in Hawaii and having a party. Well, then the thing generates this. This person looks very real. It's a completely artificially generated person. And again, that explains a little bit what these things do. They have taken a look at millions of pictures online, and based on that, you say, generate me another picture. Generate me another picture that looks a lot like all those pictures you've seen before. This person looks very real, but it's not. It's just looking at patterns that existed, replicating the patterns to a new instance, and then you get these kind of things. We've seen this video from Open Sora where you have dogs basically playing in the snow, and this is like just something that they didn't publish too long ago. But again, I mean, they're going in big following steps, because I mean, you can still see it a little bit if you look around at the feet and the ears a little bit that it's generated, but this was just generated by prompting. So by saying, okay, display me 3 dogs, young dogs playing in the snow, and you get these type of things, and then people say, wow, this is really, this is intelligent behavior. But again, all done via matrix calculations and multiplications. Where can you use it for or where is it already used in business applications worldwide? Well, for instance, you have anomaly detection. Today, if you file text applications, they will be screened for abnormal behavior. And if you have abnormal behavior in your text declaration, you will be flagged for potential fraud, and you might be investigated more in depth to see whether it's true. There have been already in the past quite some cases where some companies, some banks would look at your social network and would look at your friends, your connections on Facebook, for instance, and based on that, determine or predict whether or not you are likely to be a good client for the bank for the mortgage. Because what they assume and what they know is that if you are in a social network where all the people, most of your friends are good payers, they are reliably paying your mortgage, well, history tells us that then often the chances are good that you also are a good client and well paying your mortgage. Whereas if you are in a social network where a lot of people have already defaulted and will not be able to pay their mortgage, then the chances are bigger that you will also not be able to pay your mortgage. In Belgium this is forbidden, but still these kind of simulations, they are possible. They are, for some companies, they consider it very interesting, and they have some value. Whether they're ethically or not, it's something different. As I said before, you have sentiment analysis, but you can also do more profiling. And you have startups which, for instance, try to derive information from text that is generated, for instance, on Twitter, even if you do not disclose your age, even if you do not disclose your nationality, if you do not disclose your gender, with lots of the training data that they have and lots of label data that is already there, they can predict it. So even if you're writing tweets and you do not disclose your age, your gender, your location, or whatever, based on the amount of data and the training that they have done, they can start predicting a lot of personal information about you. What is your age? What is your political preference, and so on, can often be derived from data. And I think that's another thing you need to keep in mind, and what's very infrequently mentioned in the media or by other people discussing it. If you disclose data, if you put your picture on the internet, then most people realize that if they cross a camera, their face can be recognized. And if they put on Facebook, this is me, and they put a picture next to them, most people can understand that if they then cross a camera, that they are recognized because it's a similar picture. My name is attached to it, done. What most people do not realize is that often, if you give away certain type of information, you also give away other information that's not explicit in that data, but that can be derived from it. Most people do not realize if they write a small text that a lot of those applications, they are actually able to predict with quite a high certainty your age, your gender, your political preference, and so on. So if you were putting deliberately your picture on the internet, probably you kind of agree that people can see your picture and might even use it. But if you put a piece of text on the internet, probably you are okay with people reading the text and using it, but probably you did not want that people can actually derive what's your age, what's your gender, what's your political preference. And that's something that's often not mentioned. And so, but I personally find this very tricky because you disclose things that you are not aware of that you are disclosing. Of course, these days people use it for many more things, to do DNA analysis, to do in education, extract knowledge, to look for violations in certain justice systems, and so on. There are some quite funny failures that happened. Those systems, as I said, data scientists, they like dogs and cats. And so when they try to make the difference between these cupcakes and dogs, very difficult for artificial intelligence systems. And so are they really intelligent? Well, for a human, it's a no-brainer. We clearly see the difference between the dogs and the cupcakes. For those artificial intelligence systems, much, much more difficult. This right one is an example that was used during the COVID pandemic, when people were able to again start to do a little bit of sports, but the people from this soccer team, they were not allowed to be in the stadium. And even the cameraman was not allowed to be in the stadium. So they said, okay, we want to follow the football match, but we cannot be there. We will film it. The cameraman is not allowed. So we will put a camera there and we'll be very smart. We'll have some kind of artificial thing, and that will always focus on the football. So it will just automatically send the camera to that area where the football is. And so then we can follow the football match. Well, what happened is that in this case, one of the referees, like me, had not so much hair anymore. And so the camera was sometimes making the error by not following football, but actually the head of one of the referees. So a lot of those football fans, they were actually looking at the referee all the time, not at the location where the football was. So yes, we are making big progress, but certainly this example shows to you that it shows kind of intelligent behavior, but it does not understand. It does not understand what a dog is. It has learned to recognize a dog, but it does not understand it. And also here, sometimes you have some consequences that are not so easy to predict. Often people, to judge systems, whether they're good or they're bad, they use kind of this metric like the accuracy. So how many times, for instance, does this system recognize a dog correctly or says it's not a dog? Up to the total data set. So how many times is my system correct? How many times are the predictions correct? Versus if the system does a prediction, this is a dog, and it is actually a dog, how many times was that compared to also the false positive? So suppose the system identifies 100 dogs in the pictures. Well, 80 of them might be real dogs, but 20 of them might not be real dogs, well, then you have a precision of 80%. So these are some metrics which are then used to compare algorithms, to compare applications. Let's see, what time do we have? Other things that happened, published in New York Times, sometimes these things, they get very, very impressive in the sense that, of course, the Pope never wore this coat, but yeah, it looks very real. It looks very real. Again, the application, the algorithm does not understand what the Pope is or does not understand what this code is. You just ask them to take this person, put this certain type of code around it, and it works. It actually looks very nice. This is an example that already was published several years ago, but it illustrates, in my view, very well what might happen. This was a case where a father of a daughter, he sued a certain company because the daughter was sent advertisements for all kinds of pregnancy products, and the father was a bit he was annoyed, and he was angry because he said, you cannot send my daughter these kind of advertisements. And then actually he also said, yeah, because my daughter, she is not pregnant. Well, what turns out was that the daughter was pregnant. Father didn't know it. The daughter also never declared it, of course, to this company. The company didn't know, but based on transactions in the past, in the history, they knew that people buying these kind of stuff, they tend to be pregnant. So we will give them some advertisements for similar products. And that relates a lot to what I said before. Nobody knew that they were disclosing this kind of information. Nobody wanted to disclose that information. But when putting these kinds of raw data into a system, these systems can often derive a lot of things that you were not aware of. So you should be careful with it, or at least we should be careful as a society. Yeah, what we do with it, what is ethical use, what is unethical use, and be aware that the consequences might be bigger than we initially perceive. So some of the challenges I listed then here. First of all, transparency, explainability, opaqueness. What we see here is that it's difficult actually to explain. The point that I try to make that is it's nothing more than maths, nothing more than matrix calculations. The problem is those hidden layers, they are very difficult to understand. Here with a normal linear regression, one can assume that the bigger the house, the higher the price. Quite easy to explain. In a very nice city, higher price than in a not so nice city. But here in these neural networks, there are many hidden layers, and we don't know what they mean. We hope that they are meaningful. We hope that they can discuss or identify certain parts or subparts of a figure or of a video or an image, but we don't know. And that's scary because there's opaqueness. Suppose that you use this to determine whether or not you would like to give a person a mortgage, yes or no. If you use these kind of models, the only thing that you can say is system says yes, system says no. Most people don't like it. Most people don't like the fact that you go to your banker and you ask for a mortgage and he or she says no, and you ask why, and you say because the system says no. That's not what you want. And even now there are coming legal obligations that it is not allowed. If you as a bank refuse a customer to give him or her kind of a loan or a mortgage, you need to motivate why you decline it. So there are some ethical concerns and also some legal actions taken on that to provide or to prevent that these things are happening. There's a privacy and representativeness problem. Do we want that our data is used to train those algorithms? Some say yes, some say no. The representativeness, we know that these, as I said, it's pure math, it's pure matrix calculations. So these algorithms, they also don't have a judgment. They are not racist. They do not have any kind of prejudices towards certain ages or political convictions or whatever. They just take the data, look for patterns, and then apply those patterns again. So if your root data has kind of a predisposition, a bias towards some kind of characteristic, that will be replicated in your system. There were companies who used these neural networks to decide whether or not to hire a person. What they did was they provided training data, past CVs of data of people, and a decision yes or no hired. And then they said it's easy. We just provide new CVs and the system will tell us whether or not to hire the person. What turned out, the system was rejecting most of the female applications and approving most of the male applications. And then people said, well, the algorithm it's discriminating people because it's discriminating women against men. When they looked at the source data, they saw, well, actually, the algorithm wasn't discriminatory. It was the source data of that company that proved that that company was much more likely to hire males than females. So there was kind of a bias in the source data, in the input data, but the algorithm as such was not discriminatory. It was just replicating what was there in the input data. There are questions on the liability. If something goes wrong, who is to charge? Is it the person providing the input data? Is it the person providing the algorithm, training the model? Is it the person who uses the model? Not always very clear. And what's the degree of autonomy? These days, for instance, even in warfare, there are systems who can autonomously identify a person and to decide to attack that person based on recognizing the face, flying to the person, and drop some ammunition there. Technically, that's possible. Do we want that? Ethically, there are a lot of concerns and a lot of questions we want to have there. So lots of possibilities, lots of challenges, and of course, we need to take those into account. As in last lecture, I do not tend to take a moral stance, whether I find things good or bad or whatever. I just try to reflect what's out there, what's possible now. And of course, we need to take all those things into account, whether or not we want to apply them, whether we need legislation, whether we should do some ethical reflections.